of chapter 7, it's systems. Equations, inequalities, systems. Systems say, you know what, one equation doesn't cut it, doesn't do it, we need more than one. One equation doesn't cut it, it's not enough, we need more than one. I can give you some practical examples. I'm pretty sure most of you would tune me out if I tried to get all practical. But just to be simple about it, guys, if you started your own business, and if you were trying to analyze cost, or if someone was trying to analyze cost for you, like you weren't doing it but someone else was analyzing cost, where your money was going, where could your money be going?
Anywhere.
It could be going towards rent. It could be going towards the help that you hire. It could be going towards the production of the product. It could be going towards the transportation of the product to your store. It could be going towards promotions where you're kind of paying out of pocket to try to get customers in. Where could your money be going? Could be wasted, could be stolen, could be going all sorts of places, right? So without getting too detailed, but just thinking specifically towards economics and business, there could be a lot of different equations. There could be a lot of different conditions to consider. That's kind of what we're talking about with systems. There's more than one. Now, it's going to just be super mathy for a long time. 7-1, 7-2, 7-3, 7-4. Super mathy. 7-5, 7-6 gets a little bit practical. Just a little bit to give you a peek. Okay? We're talking in honors pre-cal today just for a second because they're in chapter 8 and it's very technical. With matrices, some of you remember a little bit from that last year. But I was like, your calculator can do it, so why am I trying to show you the behind the scenes of how it works? I'm like, well, someday I don't want you to be completely dependent on some sort of program or some other person doing your fill in the blank for you, but you actually having somewhat of an understanding of the analysis that's involved. Either the programming that goes into it, because maybe you'll be the programmer someday for some new tool, some new technology that needs to do a new task that no one's ever made before. Or maybe you're going to have to be dealing with data and research in the medical field or other places where you have to analyze stats. And to analyze stats, you have to have an understanding of the data and what's valid, what's not valid, what has a conclusion, what doesn't have a conclusion, what other people are telling you and whether or not it's something you can trust or not. So anyway, systems of equations, if it's dealing with conditions, we're just trying to think of how do you put different conditions together mathematically, showing you a little bit of behind the scenes so that you're not completely inept whenever you might face different things down the line where you have to analyze information. If you never struggle with analyzing it now and knowing why, not just what, well, it's a scary thought for our society. Joe, I'm going to answer your question in just a second. Try to remember it, okay? Kiddos, real quickly, I just want to fill in these two blanks and then move to the next page. Linear versus nonlinear. How come this is a linear system and that's not? Why are these two lines? What do you see? I'm hearing multiple things. Matthew just said because there's no x squared. Jason, what were you saying?
It's kind of like, it's the same number of like, oh no, so those are both binomials. The other one's a trinomial.
Okay, true. Technically, it didn't have to be a trinomial, but it could be. Remember, we could just have x squared and 7, and it's still nonlinear. But he's just kind of seeing the pattern, like, oh, those only have 2 terms. Those maybe can have up to 3 terms. But the more specific is that both of these have a degree of 1, right? And more specifically, linear, remember, isn't that y equals mx plus b? So couldn't we get the y alone to be an mx plus b? Oh, and isn't there a standard form called ax plus by is c? Both of them are lines. But as soon as we get over here, nonlinear, why? There are no lines? No, there's a line, but do we have some sort of nonlinear component? Yeah. It includes, doesn't have to be both, but it includes a nonlinear equation. Ooh. Are quadratics the only nonlinear equations that we've seen this year? Oh, stink. Haven't we seen trig? Haven't we seen logarithms? Haven't we seen exponentials? Haven't we seen rational functions? Uh-oh. Some of you guys might want to grab a calculator out. Joe.
Wait, for the second one, nonlinear, why? Because 2x minus y obviously is linear. Is
Right.
it just happening?
But didn't I just say includes a nonlinear component? Doesn't have to be both. Because we're talking about the entire entire system. Does that make sense, Joe? So I can't say the entire thing is only lines. I can't say that. Down here, as you guys got your calculators ready, an ordered pair that satisfies each equation in the system. An ordered pair, a point that satisfies each. A point that satisfies each. Huh. Let's go check out this. They give us two equations. It's a linear system. Both of them are lines if we were to rewrite them. Both of them are lines if we were to rewrite them. The example says, I give you 2x plus y equals 5. I give you 3x minus 2y is 4. And they say, hey, this guy's a solution. Do you agree? Well, what do you guys think? I mean, yes, it's always smart to agree with the book, but pause. They tell you to check. How can you check it's a solution? Where I both answers I just heard dealt with algebraically. Plug it in, substitution. Sweet. Plug what in? What is this? Analyze the data. Who is this? Uh-huh. It's an x and a y. Yeah? So shouldn't we be able to plug into the top and be like, oh, okay. So 2 times plus equals 5. So 2 times 2 plus 1 equals 5. True or false? Sweet. It works. Wait. For a system, yeah, for a system it has to work in both, not just one. He has infinitely many points. He has infinitely many points. But do they share any? 3 times minus 2 times. Plugging in your x, plugging in your y, I plug in 2, I plug in 1. 6 minus 4 is 4. True? Oh, I said it wrong. Thanks, Joe. No, thank you. I said it differently than I was reading it. 6 minus 2 is 4. True. But that's algebraically. How could you graphically check? Ooh, what's a snazzy math term for crossing? Intersect. How could I graph both of these lines? Yeah. Totally get y by itself. Well, plot the point and then, I think we. So the first one, I would go ahead and solve for y. Are you guys okay with a little bit of mental math if I just say y equals negative 2x plus 5? Are we tracking? Subtracting to the other side? But is the second one as easy? So I'm going to put what it is. I'm going to put negative 3 halves x minus 2. But I'm a little more worried about whether you guys could get there. Yeah. So Tyler was like, how? Okay. Does it make sense if I do negative 2y equals? Some of you it makes sense. Good. But a few of you, that's a lot of math all at once. Does subtracting the 3x make sense? Hopefully. But I wasn't done yet. What else do you have to do? Oh. Good. Is it dangerous sometimes to try to go fast? Because I had to subtract the 3x and not forget this negative and divide by a negative. Was I almost right? But it wasn't supposed to be a negative. What's it supposed to be? Positive. And is that going to make a very different line? One's uphill, one's downhill. So I erased not the part I needed to erase. There we go. Do we have it? Kind of. Now we just have to graph. So sometimes it takes a little more work than others, but guys, long story short, it's going to be very, very useful for this chapter to get y by itself. And maybe some of you need to show the work, and that's okay. Don't feel ashamed by that. Show the work. Go step by step. Remember, when you need to divide to get to y, you have to divide every piece of the, like Jason said, binomial for a line. Be careful of your signs. Some of you might be able to mental math it. Just be careful of making mistakes like I just did. How do we graph lines? We should know this. We have our intercept, right? And then we have our rise over run. But we start with our intercept first, true? So we have our 0, 5. I love to color code things, especially this chapter. So I'm going to go 0, 5 and put it up here. We're going to go down 2, right 1. 4, 3, 2, 1. There we go. Because remember, 2 can always be put over 1. Any whole number always over 1. So negative goes down 2, right 1. Got it, down 2, right 1. Got it, down 2, right 1. My other line? -2? Oh, I have to go negative. Rise of 3, run of 2, right? 1, 2, 3, and 2. Hey, that's convenient. So quick reminder, algebraically or graphically. Algebraically, plug them both in, or plug it into both, or however many equations you have. It has to work in all of them. Graphically, they're going to be intersections. Intersections, what I have you get out? Okay, pause. Where do we get graphs in the calculator? Okay, so go to y equals. How hard would it have been, bless you, how hard would it have been to plug in these lines to your calculator? Not very hard. How bad would your zoom have been, just normal zoom standard? Not bad, because it's going to include 10 by 10. It's going to include this. So let's do a quick recap, quick refresher. And if you don't remember, reach out in your group, and I'm here if your group is stuck. Do you remember how to find intersections in your calculator? Ooh, Joe's telling you where to go. Let's make sure you can get the 0.21. Not this problem. This problem was easy as far as the math. But remember, exponentials, logarithmics, trigonometrics are coming. Do you remember how to use your intersect feature? So you do y equals -2x plus 5 is y1. y2 equals 3 halves x minus 2. You would graph it in your zoom standard. You should see your intersection. Are you guys second tracing yet? Walk me through what the calculator is asking. Second trace is no, that's a menu. Pause, pause, pause. Isn't it number 5? Is number 5 the intersect feature?
Yeah, 5.
Okay. So 5 is the intersect feature. And then Joe's telling me left bound, right bound. I don't think that's for intersect, is it? Yeah, it says first curve, so be on one of the colors. Hit enter. Second curve, go be on the other color if you have the color ones. If not, sorry, on the other function. Guess, now careful, guess means go close. But hit enter on guess, because guess is not close enough. You need it to go ahead and go closer than your cursor can get. So make sure you hit enter on the guess question mark. 2, 1, we're good, right? Okay, anybody have any issues? 30 seconds to reach out to your groups. Pause. Some people in your groups don't have calculators. Just double check they're good. Okay. Say, hey guys, you good? I heard one whisper. Oh, you guys. All right, when you're ready. What? There's a whole chart, a whole table of steps 1 through 5 for plugging it in? Come on, we've been doing it forever. Remember f of x notation? The difference quotient, f of x plus h minus f of x all over h, and how bad that was for us? Okay, we've been doing plugging it in forever. Do you have to write down this whole table? No. Now, first of all, this is algebraically, right? Dealing with the equations, dealing with either plugging in the points and checking, or maybe there's a way of solving with substitution. So let's just do a quick recap. In Chapter 7 and Chapter 8, we're not just looking at what to do, but why we're doing it, and what the systematic approach is. I'm not going to teach you computer programming, but I do want you thinking through what you do, how you do it, to be like, wait, if we do have all this technology, and if we can have it do things for us, not just like in the cheating, here's the answer way, but actually like accomplishing tasks, doing computations, calculating statistics, making models, if we can have it do things for us, in order to tell a computer what to do, especially if you're in the behind the scenes, and just a hint, programmers make a lot more than those that just use computers. To some degree. To some degree. Knowing how it works is a whole lot more useful, just fiscally, than just being able to use it. You have to think through things systematically, like what's actually happening. What's actually happening in substitution, something that could be repeated over and over and over again and doesn't require creativity. Computers can only be so creative. I know there's AI, but stop. Come back. There was programming behind the AI. Okay, The system does substitution. A lot of what I'm going to teach you, you're like, I know how to do this. And I'm like, well, but do you know the system? Okay. The system does substitution. You choose one equation and you solve for one of the variables. You could tell a computer, choose one, get this guy by himself. And if it's linear, you could always say subtract and divide. You could make little formulas. Choose an equation, solve for a variable. Number 2, take whatever you just found, make it the new input, substitute, input is the computer way of saying it. Substitute whatever you just found into the other equation. And you should just have one variable left over. Number 3 says, okay, solve what you have, because it's only one variable, get it by itself. Number 4, here's a new term we're going to be using quite a bit, back substitute. What that means is you already have one value. You've gotten x to b, or you've gotten y to b. Go back to what you had earlier. Use it to find the other variable. And number 5 is just saying check. And specifically, I'm going to say for extraneous. Now, it's good to check just to make sure that all your process was right. It's good to plug in and be like, hey, this is good, right? I didn't make a mistake. But we've also seen, especially with logarithms, there can be extraneous solutions where it's like the math says yeah, but reality says no. Struggle. My quick little note says solve for the simplest variable, the one that can be isolated most simply. This is what you learned way back in algebra. However, this isn't always the case. I'm going to say usually. Sometimes if you go solving for the simplest, you're going to actually make your life a whole lot harder. Because now we're getting to much more complicated, not much more, but more complicated systems than just linear ones. All right, kiddos. Is this a linear system, yes or no? There's a circle, yeah. Now, is there a line? Okay, here we go. Hold on, pause. I want you guys to think if you were to use your calculators. You all love your calculators, right? So what if you were like, ugh, I don't want to do substitution. There are squareds. I get it. I feel you. How would you use your calculator? Go ahead. Oh, no. Wait a minute. Look at your calculators. Y equals, what do you have to have alone? Oh, no. I have to get that y by itself and that y by itself just to use your calculator? Are you sure you want to use your calculator? I'm not saying it's bad. I'm just saying maybe it's not as easy as you thought it was. Could you get y by itself? Yes. Could it be useful to get y by itself? Hey, y is the simplest variable to get by itself, isn't it? Can't I just add that to the other side? Boom, y equals? Oh, then I'm going to rewrite this. I'm going to say I don't like you, and I'm going to say y is equal to positive 1/2 x minus 5/2. Okay, y1 equals, okay, good, but what else do you have to get by itself? Is anybody tracking with me? If I show y is equal to plus or minus the square root of 25 minus x squared? Ugh, I have y1 and y2, the positive, and y3, the negative. Oh, stink, I have to graph 3 things? But if you're using your calculator, remember the condition I said. If you're using your calculator to get what you see here, you would have to have the positive square root, which is the top half of the circle, the negative square root, which is the bottom half of the circle, and the line. You'd have to do y1, y2, y3 after getting y by itself. Ugh. Is it possible? Yes. Is it your favorite? Maybe not. Wait a minute. Did we have to use our graphing calculator for this? No. No. Why do I have a picture up here of a line and a circle? I said, hey, I could graph this line. I could make it with an intercept of negative 5/2. Okay, it's negative 2.5. I'd have to be kind of careful with that. I could go up 1 over 2, if I can get my points in the right spot. Sorry, everybody. And I could graph this. Wait a minute. Should we know this is an equation of a circle with a center of 0, 0, and a radius of 5?
Yeah.
Oh. So maybe if I drew this very, 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 very carefully without having to do all the but do you know exactly where this falls? Is it -4, -1? Is it -3, -2? Is it decimals? Ooh. So what would substitution say to do? We already have y isolated. Why not just go plug it in? But how many of you guys realize this doesn't look so fun? Oh, sorry, not plus, equals 25. Who's going to have fun with this? Oh, you are? Could you do that? Yeah. Could you FOIL stuff with fractions? Yeah. But do you remember back here I said usually? Can I help you out just a little bit? Is that okay? Can I help out just a little bit? Okay. Was it bad getting y by itself and plugging in? No. But what are you now going to be really sad about? Getting x alone. You're like, oh no. Right? So what if instead we said we don't like fractions? Who wants to say an amen to that? Who doesn't like fractions? The rest of you guys love fractions. Oh my goodness, I don't believe any of you. How do we get rid of fractions?
Multiply by the denominator.
Can't we multiply everybody by 2? What happens when you multiply by 2? Well, isn't that going to be -x plus 2y equals -5? Anybody with me?
Yeah.
To get y by itself would be useful for the calculator, but we just saw that was nasty. To get y by itself would be useful for a graph, but man, we better get graph paper and make this precise. Maybe we don't want to get y by itself. Maybe I want to get x by itself. Hey, there are no fractions if I get x by itself, right? So what if I add x to the other side and add y to the other side? I get x is equal to 2y plus 5. Why do I like that substitution better? Fractions are gone. Right? Do you think maybe you guys would make fewer mistakes by foiling this than you would foiling that other nastiness that we just saw? Because now, okay, don't kill a puppy, but as long as you don't kill a puppy and you actually do outer and inner and you put them together, that'd be 20y plus 25 plus y squared equals 25. That would be 5y squared plus 20y. Is anybody okay if I cancel out the 25s? Because if I subtract it would be 0. If I factor out a 5y and get a y plus 4, kiddos, how am I doing? Yeah. And now if we have factors equal to 0, don't I just set each one equal to 0 and say, hey, y is 0 or y is -4? Does that make sense if this point has a y of 0 and this point has a y of -4? Could be. But I need to find both points. So what's now my goal? Back substitute. You have y's. What am I going to do? Ding, 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 ding. Go find x, right? Go back and say, okay, I have an expression. So let's go ahead and say who is or what is x when y is 0? Who is x when y is -4? Guys, I'm using function notation. X of, not times, x of, like f of. Plugging in y is 0. I get 2 times 0 plus 5, which is 5. And I get 2 times -4 plus 5, which is -3. What do I have? My points. The point 5, 0, x and y, and the point -3, -4. Which if you had graph paper and you very carefully graphed your line with your circle, you would have seen as the intersections. What am I trying to help you with? Understanding there is a system to substitution. We do, if we need to solve. A, the calculator isn't always easy. B, graphing isn't always precise. C, solving algebraically is. There is a system for us to follow, but we can still be creative and say, I don't like fractions. Can I avoid them? And that's probably safe. So, right? What do you guys think we should do? Should we solve for the easiest one right away and say, okay, whew, we can solve for y easily. It's going to be 3/4 x minus 4. Let's go plug it in. Could we do that?
Sure.
We could. But do you guys have an alternate creative approach that might make life a little bit easier? Sure. Do you want to get rid of it in the top or the bottom? Either one's okay. Okay. Oh, we heard both. Bottom, I would have done times 4 on both sides, right? Top, why am I also going to do times 4 on both sides? Yeah. If I multiply 4 over 2, doesn't that give me something good? And then if I multiply 4 here, don't the 4's go away and I get 3y? Oh, nice. Oh, wait a minute. Now what? Do I want to solve for x or solve for y? Not really. He's pretty. Okay. Well, who do you want to? Do you want to solve for y and plug in? Or do you want to get rid of the fraction here too? We could, couldn't we? Couldn't we multiply him by 4 and multiply him by 4? And that would be 3x minus 4y equals 16. Oh, this is starting to look like an elimination problem, which is actually section 7.2. That is a valid technique, but didn't we just make it harder on ourselves for substitution? Okay, well, we tried. That didn't really make anything easier. I think we just kind of got to go for it. But can't we go? And can't we say, okay, we did what we could. We have to eventually solve for somebody. So y is equal to 3/4 x minus 4. It's not perfect, but it's a lot better than it would have been a second ago. So I have 2x plus 3 times 3/4 x minus 4 equals 40. I know it's not perfect, but it's better than it would have been. So if I distribute 9/4 x minus 12 equals 40. If I add 12 to the other side, if I, help guys, strategy. Do I want to put 2 and 9/4 together just in my head real fast? I mean, I do, but can't I make that 8/4 to make my life easier? So then 17/4 x. Okay, that was just quick algebra. How do I get rid of a nasty coefficient like that? Multiply by, well, yeah, you could just multiply by 4, but you'd have more work. I think the reciprocal is a lot easier. What you do to one side, you do to the other. And if, God's smiling down, just kidding. He does that whether or not it's good or bad. He's looking out for us no matter what. But it is going to be nice because 17 does end up going in, doesn't it? Or does it? Does 17 go into 52? No. Oh, well. Are we scared of it? No. What are we going to do? We're just going to multiply and do 208 over 17. Can we have nasty numbers? Yeah. But what are we still going to do even if we have nasty numbers? Find them, make sure our math is good, but still just follow the procedure to finish off the system. You guys can go ahead and go. I'm going to go ahead and back substitute just to finish off my problem. But homework, see what you can do. Yeah, just the reference sheet on the back, Sam, if you don't mind. Thanks, kiddo. I'll take it. Thank you. Can you pick it up at lunch?
I leave after 4.
Oh, bummer. I don't have a TA till then. Okay. Come back right at the end of nutrition. Yeah, just so I can finish this example real quick and then I'll get it.